Hi, my name is Gabriel Moreira and I'll be presenting the paper Hyperbolic versus Euclidean Embeddings in Few-Shot Learning, Two Sides of the Same Coin. In this paper, we address the use of hyperbolic geometry to embed images. This strategy initially appeared as a way to embed data assumed to have a latent hierarchical structure, such as knowledge graphs, words, ontologies, or taxonomies. And the reason for this is that hyperbolic space grows at an exponential rate, just like a tree with a constant branching factor. And so hyperbolic space is better equipped to encode the local similarities of the graph, that is to say the local distances, and preserve the neighborhoods, as we can see here in these two images comparing Euclidean embeddings and Poincaré, which is a specific type of hyperbolic embeddings of the same tree. In computer vision, hyperbolic geometry was introduced under the hypothesis that it would help capture hierarchical visual features and thus help improve generalization and few-shot recognition abilities. Despite the good results produced in the literature thus far, it remains unclear the role that hyperbolic geometry plays. And in this paper, our hypothesis is that in high dimensions, prototypical learning in hyperbolic space actually produces embeddings that are angularly distributed, that is to say, at the same radius. Overall, we show that first, in high dimensions, the volume of an hyperbolic ball is concentrated close to its surface, so just like the curse of dimensionality in Euclidean space. Then, we show that the few-shot accuracy of previous hyperbolic encoders can actually be attributed to the angular separation of the embeddings. And finally, we show that an Euclidean encoder equipped with Euclidean metric can actually surpass the performance of previous hyperbolic baselines. To get started, I'll first review hyperbolic geometry. Hyperbolic geometry has several models. Two of the most commonly used are the hyperboloid model and the Poincaré ball model as represented here on the right. To define the hyperboloid model, we need an ambient space that is d plus 1 dimensional, and we introduce here a bilinear form G. If we consider then an hyperboloid, or the upper sheet of an hyperboloid in this space together with this bilinear form, we obtain a negatively curved space that is known as the hyperboloid or the Lorentz model of hyperbolic space. The Poincaré ball model is then obtained by a stereographic projection of this hyperboloid. And it's precisely this Poincaré ball model that we'll be using throughout the presentation. So now, if we have an image encoder, the way that we can obtain hyperbolic embeddings, one of the most common used ways, is through an exponential map. So the output of a convolutional backbone is interpreted as being Euclidean embeddings lying at the tangent space at the origin of the manifold, and the exponential map projects these tangent vectors back to the manifold itself. In practice, this exponential map is simply a rescaling of the magnitude of the embeddings, accomplished through an hyperbolic tangent. And once we have embeddings that lie in the Poincaré ball, we then apply a loss by using an hyperbolic metric. In this case, the prototypical loss would correspond to computing centroids and then spreading them apart. And this is what we'll be looking at in more detail now, what happens in this representation space. Just as we have the curse of dimensionality in Euclidean space, in hyperbolic space something similar happens. That is to say that if we compute the ratio of the volume over the area of an hyperbolic ball in high dimensions d, this ratio will tend to 0 as d grows. So the volume of a ball will be roughly concentrated close to its surface. And the second fact is that if we have two embeddings lying in the Poincaré ball roughly at the same radius or numerically at the same radius, then the distance and thus the similarity between them becomes a monotonic function of the angle that separates them. And this is precisely what also happens in Euclidean space. And to see this in more detail, consider here a comparison between the squared Euclidean metric, the Poincaré metric, and the Euclidean metric for embeddings lying at the same radius, ranging from 0 to 1, and having an angle between them, theta, ranging from 0 to pi. We can see here that the squared Euclidean is considerably different from the Poincaré metric. And note that the squared Euclidean metric was the one typically used in prototypical networks that were compared against hyperbolic space. However, if we compare the Poincaré metric in the center with the Euclidean one on the right, we also see that the latter becomes a good approximation of the hyperbolic distance. So what do we propose? We propose to replace the exponential map, which was accomplished, remember, by that hyperbolic tangent, by a simple rescaling of the vectors so that they all lie at a common radius. And then we discard the hyperbolic metric and replace it by the Euclidean distance. And this is what we call the fixed radius Euclidean encoder. To validate our hypothesis and the proposed model, we conducted few-shot classification experiments on two popular datasets, the BERT dataset and mini-ImageNet, in two settings, one-shot 5-way and five-shot 5-way, following the literature. In this slide, I present the results for the BERT dataset, where we consider different manifold dimensions and three architectures. The standard prototypical network with a squared Euclidean metric represented by RDL2 squared, then two Poincaré architectures with different curvatures, minus 0.05 and minus 0.01, and finally, highlighted in blue, our proposed model. In addition to the test accuracy, we plot the embedding radii. Note that across all dimensions, our test accuracy improves both the standard prototypical network and the Poincaré architecture, and as predicted, the embedding radii are constant even across different dimensions. In mini-ImageNet, a similar phenomenon can be observed. In this case, the embedding radii of the hyperbolic representations is not constant for the smaller dimensions, but it converges to a common radius as the dimensionality increases. In conclusion, in this paper, we set out to show that the few-shot accuracy of prototypical hyperbolic networks can be ascribed just to the angular separation of the embeddings. In addition, we showed that just a fixed radius Euclidean encoder can actually outperform these hyperbolic representations without any of the difficulties presented by Riemannian optimization on a negatively curved manifold. Overall, this does not mean that the data itself does not have a latent hierarchical structure, as these data sets both have hierarchical structures stemming from the semantics, but that the data can actually be represented accurately on Euclidean manifolds. For reproducibility purposes, the code is available online. Thank you.